Our fleet can't wait for good weather. There are schedules to meet, miles of coastline to patrol, our nation and others to protect. 24 hours a day, year in, year out, the fleet must operate. And now there are fewer ships to cover greater areas, less men, bigger responsibilities, a challenge that demands flexibility, quick response, and more speed at sea. After years of research and development in the United States Navy, we have a ship that can meet that challenge. A ship to be considered when strategic plans are made. The Hydrofoil, a ship whose time has come. Pegasus, PHM-1, is the first ship in a new class of hydrofoils. A class designed to support the fleet with speed, powerful weapons, and the ability to operate in virtually any sea. Pegasus is lifted above the water by her foil system, sharply reducing drag, flying through waves that slow a destroyer. Ready for missions once handled only by major combatants and thousands of men. Although hydrofoils are considered an advanced design, they were discovered many years ago. In 1898, Enrico Forlanini built a hydrofoil that could make 40 knots. And in 1918, Alexander Graham Bell and Casey Baldwin tested the HD-4. The HD-4 held the hydrofoil speed record of 70 knots until 1962. The Navy has been studying hydrofoils for almost 30 years. We have put foils on a variety of platforms in our search for speed and stability. But this little boat proved the turning point. Sea legs showed the advantages of foils that are fully submerged and automatically controlled, foils that allow a ship to operate in the open ocean. There are two types of foil systems, the fully submerged and surface piercing, the kind used on many commercial hydrofoils. Surface piercing foils penetrate only the surface of the water, lifting the ship as speed increases. The system is fundamentally stable, but its rough ride in heavy seas is unsuitable for Navy operations. The fully submerged system puts foils completely below the water on struts. An automatic control system maintains flying height by feeding information through a computer to the foils. Hydraulic actuators position the control surfaces to the best angle for flight, allowing the ship to bank in turns and to fly smoothly even in rough water. The distribution of foils along the hull also differs with design. The canard configuration puts large foils aft of the center of gravity. In the airplane or conventional configuration, the foils are forward of the center of gravity. In both cases, a third foil is required for control and stability. Extended foils and struts act like deep keels and give a hull-borne hydrofoil the stability of a much larger ship. Foils are retracted hydraulically for maintenance and to reduce draft when hull-borne. Diesel or gas turbine engines provide power for hull-borne speeds of 12 to 13 knots. During foil-borne operations of more than 40 knots, only lightweight marinized gas turbines are used. Propellers and water jets are the thrust-producing choices for hydrofoils. Water jets eliminate long mechanical transmission systems. However, they require more power than propellers. Water jets were chosen for the PHM, both for hull-borne and foil-borne thrust, but any combination could be used. Hydrofoil hulls are designed for strength and good seakeeping. They are constructed to withstand large waves and emergency landings. Hulls like this, and those of all Navy ships, are tested at the David Taylor Naval Ship Research and Development Center near Washington, D.C. Model basins recreate actual sea conditions, allowing engineers to see how hulls behave long before construction begins. People work on materials, piping systems, structural tests. An effort with one goal, a ship that will serve the Navy well, the finest ship that technology can produce. At the center, the Advanced Hydrofoil Systems Office works with engineers and technicians, planning trials, exploring missions, evaluating data. To verify the information learned from models, to evaluate new equipment, missions, and training methods, the center uses Plain View and High Point, based at the Puget Sound Naval Shipyard in Bremerton, Washington. Plain View was designed by Grumman Aerospace and built by Lockheed Shipbuilding Company. At 212 feet long, she is the largest hydrofoil in the world. Plain View is fully instrumented for trials documentation and usually carries civilian technicians from Navy laboratories as well as her regular crew. She was built to evaluate the potential of large ocean-going hydrofoil ships. Plain View and High Point have important jobs: to test and evaluate equipment and systems for fleet hydrofoils like the PHM. And because studies result in new discoveries, the ships themselves must be modified and improved. And a major overhaul means more than paint, updated equipment, and interior changes. High Point, the Navy's oldest hydrofoil, was delivered by the Boeing Company in 1963. She has logged hundreds of foil-borne hours and is a major contributor to the development program. Flagstaff is a gunboat 74 feet long. She was designed and built by Grumman and served in Vietnam with her sister ship, Tucumcari. Flagstaff recently was turned over to the Coast Guard to begin a new career. Tucumcari was designed and built by Boeing. She toured Europe in 1972, demonstrating hydrofoil capabilities to NATO nations. This performance was so impressive that Germany and Italy agreed to share the development costs for a hydrofoil design, giving each a new naval capability at less expense. The operating experience from these 4 ships set the stage for the design and construction of the PHM, the Navy's first missile-equipped patrol hydrofoil combatant. This is the first ship built as a multinational project and the first U.S. Navy ship built to metric specifications.
Of America, I christen thee Pegasus.
Pegasus was launched in November 1974 in Seattle, Washington, where she had been designed and built by Boeing. Pegasus has many of Tucumcari's features, such as water jets and canard configuration, but she is almost twice as long, 40 meters, and her electronics equipment is far more extensive. Once foil-borne, the automatic control system requires no decisions from the helmsman. It makes allowances for turbulence, trim, and altitude, and banks the ship in turns. The fully swiveled strut on the forward system provides agility and excellent turning rates, even in heavy seas. Hull-borne, water jet nozzles pivot in response to the helm. Buckets provide reversing control. A bow thruster supplements the nozzles and makes her easy to maneuver. Down below, the crew can eat, sleep, and work during operations. Normal conversation is possible. In the engineering operations station, a single engineman monitors and controls the main and auxiliary machinery and the entire electrical plant. Machinery spaces are unmanned except for routine inspection. Eight Harpoon missiles will be carried in 2 clusters on the fantail. Harpoon is an all-weather surface-to-surface ship attack weapon. Wings on the missile fold inside a canister. The canister serves as a shipping carton, then protects the weapon during normal ship operations. Missiles are activated from the Combat Information Center. PHM's 76mm gun is lightweight, automatically controlled, unmanned. Up to 80 rounds a minute can be fired without reloading. The fire control system can track several surface and air targets at the same time, fire both the gun and the harpoon, and be used for navigation. This ability to fire guns and deliver missiles while flying at 40 knots is due to development trials on other hydrofoils. Trials with guns. Torpedoes. Trials with missiles. Trials with towed systems for anti-submarine warfare. Through these trials, hydrofoil experts learn that the best way to service a small ship is to bring her home. A mobile support group, now based ashore, provides the PHM with quick turnaround. She can be refueled, supplied, and repaired within hours. At sea, a squadron of PHMs would be served by a support ship. They could range far from land, their guns and missiles ready for action, providing the Navy with a whole new area of flexibility. PHM and others in her class will augment surface forces, particularly in offshore coastal areas and narrow passages where larger ships can't maneuver. The hydrofoils could loiter, hull-borne, for a week or more, return for supplies, and resume operations. During wartime, they could detect and attack enemy forces, be used for blockade operations or in convoy duty. They could free larger ships for duty in the open ocean. A ship can have speed. She can have powerful weapons. She can be seaworthy. But she will never leave the dock without people. The hydrofoil program is characterized by special people, adaptable, innovative, skillful. Several crew members have developed effective ship improvements, like this tactical navigation system on High Point. The system allows the navigator and the helmsman to see their ship's position relative to others, all superimposed on a chart in real time. In the future, we expect to build faster, larger hydrofoils. Hydrofoils that can cross the ocean without refueling. Ships that consider speed and rough water a way of life. This technology will be extended to the civilian world, so it too can travel fast and smoothly in all kinds of weather. The fully submerged system developed by the Navy's research program is being used successfully on new commercial hydrofoils. Ships like these, with speeds up to 50 knots, are carrying passengers in Hawaii and Hong Kong on routes where rough water and blustery weather are common. As the oceans grow smaller, we need a ship that is fast, efficient, and reliable. A ship that can cover vast areas in a short time, armed with powerful weapons, manned by a small, well-trained crew. The Navy has taken the careful developmental route with the hydrofoil, a concept that now is a reality, a ship whose time has come.